So what we got to realize here is when we're graphing this quadratic, this parabola here, is we got to remember like its parent function. Okay? And what I mean by that is our a value, our, do you remember h and k? Yeah, and our k value. Okay. So first of all, we need to define what is what. What is my a value in this one? Yeah, my h value. And k. Okay, good. Now we got to talk about how these transform a graph. Okay, a deals with stretching and compressing, right? So stretch, and compress, and also does flips, right? In case it's negative or positive. H deals with moving it left or right, the entire thing. And K deals with moving it up or down, the entire thing. Our original function is f at x is equal to x squared, or y equals x squared. Okay? So the way we graph that is our vertex is at 0, right? And normally we go over 1 and square that. 1 squared is 1, so I go up 1. That's my next point. Same if I were to go this way. I go negative 1 from the vertex, and I square negative 1, I get positive 1. There's my next point. And then from here, back at the vertex, we go over 2. 2 squared is? Yeah. Negative 2 squared? No. Yeah, positive 5. Let's say we go over 3 from the vertex. 3 squared is? Yeah. And then negative 3 squared? Okay. So this is our original function. Okay, this is the original parabola. So we have f at x equals x squared. That's our function. Okay. Now, like we talked about before, there's several things that are happening here. First of all, we can deal with the stretch first if we like, and then move the entire function, which might be helpful. The stretch here, remember what I was talking about when we go over 1 and we square it? Whatever we square by, we technically multiply by our a value. So a value. The a value here is 1, right? So no matter what I square by, 2 squared is 4. 4 times 1 is still 4. 1 over squared is 1. 1 times 1 is still 1. When I go over 3, 3 squared is 9. 9 times 1 is still 9. So it doesn't change anything with our original one. But when we're talking about a and it's a different number, okay, we call the red one our red transformation. If I go over 1, square it, 1 squared is 1. Then I multiply by 5. So I go over 1 up 5. Okay. See if I go in the negative direction. Negative 1 squared is positive 1. Positive 1 times 5 is, let's talk about 2. Over 2, what's 2 squared? 4. We go up 4, but what's 4 times 5? Boom, we're way off this already. Okay. So let's say we're just doing this transformation. Okay. This is the type of graph we would have. Very stretched in comparison. Okay. Well, this is only one transformation. This would be f at x equals 5x squared. That's our red one. Okay. Now, what I'm going to do actually, since we're going through graphing, I'm going to go through each of these individually and then put them all together. Okay. H is negative 3. Okay. So normally, actually, you know what? Let's go to k because it's an easier number. K is positive 1. That means we move the entire function up 1. So we don't stretch anything. We're back at the black one, which is our original. We take the vertex and move it up 1. Take this point here, move it up 1. This point here, move it up 1. This point here, move it up, move it up. This point here, move it up, and move it up. Okay. It's still the same shape. It hasn't been stretched. It's just moved up 1. So this is like the black one, the parent function, just shifted up 1. And the reason it's the same is that if we go over 1, we still go up 1. If I go over 2, I go over 1, 2, 3, 4. Perfect. I go over 1, 2, 3, 4, 5, 6, 7, 8, 9. See how it's still the exact same function as the red one? Or sorry, the black one. The red one's much different. And finally, from the original, h is an opposite idea, right? We have negative 3. We don't go in the negative direction. We actually go in the positive direction. So we shift the black parabola 3 to the right. So our vertex is now at positive 3. I go over 1, up 1. From there, and I just kind of redraw everything. Over 2, how many do we normally go? Let's do it here. Over 2, up 4. Over 3, up 9. Over 3, up 9. So the blue one would be f at x is equal to x minus 3 squared. The green one would be f at x equals x squared plus 1. These are all just one movement, okay? Now what's actually happened here is we're going to redraw because it's very confusing right now. We're going to put them all together. Okay. So instead of drawing the original one, we're going to draw them all put together. So first off, our vertex goes from the 0 point to the 1 point, right? So we already know we have to go up 1. That's our k value. Our h value, it says negative 3, but what direction do we go? To the right. So we go in the positive direction. 3. So here's our new vertex. They're essentially telling us our vertex, right? And the h and k value are the vertex. I'm going to show you how. Your vertex is it's now at 3 and 1, right? Well, your k value was 1. Your h value was negative 3, so it's just kind of like the opposite of your h value. Okay, so we have that. And now all we got to do is stretch this function. Go over 1, up 1. But how many do we really got to go up? Because we got to multiply by 5. Yeah, so we go over 1, up 5 from there. So 1, 5. That puts us at this point. Over here, up 5. The next one's going to be way off the chart. We have a thin parabola with a vertex at 3 and 1 that is very stretched. So that's after we've put all those ones together, that's what our new parabola looks like. Okay, so now for this function, they're asking me for domain and range. Domain deals with how far along the x-axis it's going to go for, both ways. Because there's arrows, will this one ever stop? No. So our domain for this one, domain, x is the set of all real numbers, xer. That's our domain. Okay. Now our range. Same idea, this is a continuous function, so it's going to be yer such that there is a restriction. What's the restriction on this function here? What is it? 1. Is y going to be greater than or less than? Yeah, that's right. It only exists above 1. Anything below 1, there is no function there. So y is every real number such that y is greater than or equal to the number 1. That's the domain or range to that function there. So to tell if this is a function by looking at the graph, if I draw vertical lines everywhere, if it only touches this points of this graph only once, that means it is a function. Now if I had something like this and I drew vertical lines, this would not be a function because it has 2 values. Okay? So we know it's a graph by vertical line test. Line test. That's how we know by looking at it. Okay? From looking at its equation, if I were to plug values in for x, so if I plugged, let's say, 1 in for x, I wouldn't get 2 y answers, like 2 or 3. If I got 2 or 3, that means it wouldn't be a function. If I plug 1 in, we know that it's 20 or something here. Or if I plug in the number 2, the only y value is 6. So it's 2 and 6. Okay? So when we plug this in, so when putting x in, x, get only one output for y. So it should say when inputting. When inputting x, we get only one output for y. Okay, that's how we know by its equation. So okay, so we went through this function. They gave you f at x was equal to, what was it? Negative 5 t squared
plus 8
t.
18, sorry, 18.
Yep.
Plus 0.5.
Okay. Now we plotted all these. We substitute these values into f at x, and we found out these are our y's. So we have to graph this. What these are these are all coordinates, what they've given us. This is a coordinate, this is a coordinate. And imagine them like x and, instead of f at x, but instead they're x and y values. So we go from 0 to, actually we go from negative. Let's say this is our 0. We go all the way up to 16. 16.5. Okay, perfect. We'll go 2, 4, 6, 10, 12, 14, and 16. Okay. Our very first point, 0 and 0.5. That's like here. Okay. 1 and 13.5. That's probably here. Let's get our 1, 2, 1, 2, 3, 4, 5. Okay. 2, 16.5. So let's say it's about there. 3, 9.5, probably about there. And 4 is actually negative 7.5. So assuming this graph continues down, let's go with this. If we're at negative 2, negative 4, negative 6, negative 8. Negative 7.5 is down here. So when I connect the dots for a curve of best fit, I have something that probably looks like this. Okay, and this is the flight of the ball. What they're saying is, remember this was a football. Football's been kicked. They kick it way up into the air. It comes down, and then when it crosses the x-axis, what does that really mean? Yeah, it hits the ground. It doesn't go through the ground, right? It doesn't have that type of power. But that's when it stops and hits the ground. So this is what we've graphed. We got our points, and we've put a line of best fit through it. This is the equation that models that. So we know it models that. So we know. So we've made some educated guesses. We think the max height's probably about 16.5. You know what? Let's say it's even a little higher. Let's just go nice and round. It's about 17 meters. Okay. Let's say it actually comes up and it's coming down at that point. And then we'll say the ball's in the air. Estimate again about 3.5 seconds. Okay, these are estimates. They're pretty good guesses. Express the domain and range. Okay, this is actually a little tricky. Technically, now if this was a parabola that continued this way, our domain would just be XER, right? That would be our set notation. D funny bracket XER. But because this ball is kicked at 0 seconds. Can the ball exist before 0 seconds? Can it be in the air at negative 1 second? So before it was kicked? No, that doesn't make sense. So we do have a restriction. Our x must be greater than and equal to what number? 0, right? It doesn't go into the air until after 0. Sure, it could keep going down maybe. And if you really want to be true with it, let's say that the parabola actually stops at 3.5. That's when it hits the ground, right? So if that's when it hits the ground, it actually should read that x is in the air between 0 and 3.5. So we would put 0 greater x less than equal to 3.5. Because technically this is where the parabola stops, right? It doesn't go through the ground. The ball stops there. Then the same idea with our range. Our range is YER, but we have a high point, which we set as 17, and we also have a low point, which is what? Well, that's in seconds. We're talking about the y-axis. What's the lowest point it hits? 0. So again, such that y is greater than or equal to 0, but less than and equal to 17. Okay? Because both of these, they don't exist before 0, and they don't go through the ground, and it only stays in the air for 3.5 seconds, and the highest it goes is 17. So those would be our domain or range for this question.